Okay, welcome to the last lecture for Comp 9444, Neural Networks and Deep Learning. So this is going to be a fairly short one today. I'm just going to try to give a brief overview of the course, or try to revise what we've done and tie it together, and tell you a little bit about the exam. So as you recall, the assessment for the course is 40% assignments and 60% exam, and you have to get at least 40% in each component and then a 50% when you add them up. This is the topics that we planned at the beginning of the course to cover in the relevant sections in the textbook. And this is, I believe, what we actually covered. So I think we did a pretty good job of covering what we intended. Now, some of these are not examinable. They're just kind of added in for a bit of extension material. So the first chapter, which is on the first component, which is on neuroanatomy, and the last two items, the coevolution and the evolutionary art, are not going to be on the exam. They're just kind of extra material. 1, 15, and 16, but everything else will be covered. Now the final exam, it'll be a 2-hour exam. It's centrally managed. I think it's on, is it on Thursday, the 8th of November? Is that, I don't want to get it wrong. Okay, yeah, Thursday in the afternoon, yeah? Yes, okay, good. You're not allowed to bring the textbook or course notes into the exam. You can bring a calculator if you wish. Has to be a UNSW approved calculator, so you've got to go down up to New South Q and get a sticker on it. If for some reason you did forget to bring your calculator or you don't have a calculator, you shouldn't worry. You should be able to do the exam without the calculator, but you're welcome to bring one if you want to. Now, the material for the exam, the exercises and the quizzes on the course website give a good indication of what kind of questions to expect on the exam. And several of you have asked, and so I have actually provided a sample exam, and it's on the course website. Maybe you have to log in to see it. So I put it under the lectures here. So you've got the course review lectures and then the sample exam. Now, if you have a look at this, it's not very useful. Let me go somewhere else. Let me try to open it with preview. See if we can view it this way. Right, so you can sort of see it's a 2-hour exam, and if you look through this, some of these questions are copied directly from the quizzes. Some of them are not quite from the quizzes, but in a similar style, and some of them are quite similar to the exercises with slight variations. Yeah, so have a look at that, and let me know if you have any questions. In addition, I've put up an additional set of quizzes on the course website today. If you click on quizzes, let me see. So there's 8 quizzes now. So this last quiz just covers this last material from weeks 9 to 12, or actually probably 9 to 11 because the 12 was the extension material. Okay, so we started by looking at the structure of the typical neuron. So it had a dendrite, it had dendrites and it had an axon. And then we talked about how connections could be excitatory or inhibitory between neurons. And when the voltage in the neuron reaches a certain threshold, then a spike train or spike goes along the axon to other neurons. And then we looked at mathematical simplifications of the neuron. So this was the McCulloch and Pitts model of the neuron. Sorry, I think we haven't used the air conditioning before, but I think we may need it today. It's a little bit warm in here. So we add up the inputs, and each input is weighted. So we take a weighted sum of the inputs and check whether it's above a certain threshold. And it's a mathematical convenience. Often, instead of adding subtracting a threshold, we add a bias and then check whether the answer is bigger than 0. And for the perceptron, then we have this transfer function. So for the perceptron, the transfer function simply is the Heaviside function. So this was +1 if this weighted sum is positive and 0 otherwise. And then we talked about this perceptron learning rule, where we're presented with items one by one. And we have a learning rate, and we look at if our existing perceptron classifies the item correctly, then we don't change the weights. And if it classifies it incorrectly, we make this adjustment to the weights. So depending on whether it was positive and should have been negative, or negative and should have been positive, we add the learning rate to the bias, and we add the learning rate multiplied by the corresponding input to each weight. And Rosenblatt proved that if the data are linearly separable, eventually this algorithm will successfully learn all of the data. Then we looked at limitations of perceptrons. So many common functions are linearly separable, but some are not. So the simplest example of a non-linearly separable function is this exclusive OR function. We talked about how you could hand code. If you know the logical expression for a function, you can hand code a multi-layer perceptron to compute it. We could always do this if it's in conjunctive normal form. We can always do this with 2 layers. But then we wanted to look at how this could be learnt by automatically, which is what led us to backpropagation. Okay, so then we moved on and looked at types of learning. So the course was actually separated out into these 3 sections quite nicely in a way. So the first few weeks were supervised learning, and then roughly weeks 8 and 9, I think, 7 and 8 were reinforcement learning, and then 9, 10, and 11 were different kinds of unsupervised learning. And you should be familiar now with the 3 different paradigms. So supervised learning has told what the answer should have been. Reinforcement learning, you're not told what the answer should have been, but you're told in some sense how good your answer was, or your sequence of answers in terms of getting a reward. And unsupervised learning, you're not really told anything, you're just told the inputs, and you have to extract some structure from those inputs. Now in supervised learning, we talked about Occam's razor, which is fundamental to all machine learning paradigms. So we want to make a trade-off between the complexity of the model and how well it fits the data. So that's a simple model but doesn't fit the data well. This fits the data well but a little bit too well. And we're always looking for this kind of compromise in the middle. And we looked at multi-layer neural networks. So we first looked at these kind of old-fashioned two-layer neural networks where we have input and then a hidden layer and then outputs. And we talked about how training a neural network can be seen as a kind of local search in weight space. So we imagine that we're adjusting the weights, and for every set of weights there's a particular cost, value of the cost function, and we're ideally trying to get down to the lowest possible cost function. Theoretically, we could get trapped in a local minimum, but there's a lot of debate about this. You know, it seems like in a lot of neural network, well, if you have the right kind of activation function and the right kind of architecture, you often get a pretty good result. It may not actually be the global minimum, but often is sufficiently low cost for our practical purposes. So this was like the key step in going from the perceptron learning up to backpropagation, was making the transfer function differentiable. So the original transfer function was not differentiable because it was flat almost everywhere. So if we want to make it smooth and differentiable, the cost functions that became common were the sigmoid function and the hyperbolic tangent. And then you can write a cost as well, in this case, the squared error. So you take the difference between the actual output and the target output and square it, and you add that up for all the items, and that gives you a cost function. And then we have something that we can differentiate, and you apply gradient descent to train the network to have a low cost, right? And so we use backpropagation and the chain rule to compute all those derivatives, to compute the derivative of the cost function with respect to each individual weight, and then we subtract from each weight the learning rate multiplied by that partial derivative, and we talked about the difference between online and batch learning. So often we do this just not for the whole training set at once, but just for a single item or a mini batch of items, which is why it's sometimes called stochastic gradient descent. And then we looked at some variations on this basic algorithm. So cross-entropy, weight decay, and momentum. And if you remember, in each case, we provided a kind of we provided a mathematical explanation, but also a kind of intuitive explanation, right? So the cross-entropy, the intuitive explanation is that least squares error function is unsuitable for classification problems where the target is bounded between 0 and 1, particularly in cases where it's asymmetric, where, you know, there may be lots of, you know, not 100 zeros for every one, for example, with fraud detection and so on. In that case, it makes sense to replace that squared error with something that blows up logarithmically instead of being bounded. But then we went through this explanation of how you can actually derive this mathematically from the theory of maximum likelihood. You know, if you interpret the output as a probability, then we can interpret the cost function as the probability of getting the wrong answer, or maximizing the probability of getting the right answer. And then weight decay. So this was, we introduced Bayes' theorem. So where we additionally, as well as we have a prior probability on the size of the weights, and we say that we think smaller weights are more likely to occur than larger weights. And so we add an extra term in there to take account of that. That's the mathematical theory, and then the intuitive explanation was, well, when the weights get too big, especially if we're using a sigmoid or hyperbolic tangent, when the weights get too big, then learning kind of stops because we're in that flat region of the activation function. So this weight decay has the effect of preventing the weights from blowing up too much. And finally, we had momentum, where we had this explanation about things oscillating in a rain gutter, or perhaps just very, very flat regions with a very small gradient, and then you want to accelerate the movement across those regions. So this was the equations for cross entropy. So this is our cost function. We described how you're going to interpret this as a probability, and we looked at how this actually simplifies the partial derivatives. So we went through this whole thing with Bayes' rule. The probability of A conditioned on B is the probability of B conditioned on A times the probability of A divided by the probability of B. So it brings this prior probability into the equation. And we showed how this relates to weight decay. So before we see any data, we assume that the probability of a particular weight has this Gaussian distribution. And so when we take the log of that and the log of the other thing, we end up adding these two terms together to get the cost function. And there's always this weighting. We have to decide how much emphasis to put on the weight size compared to the error. So we have to have this parameter of lambda. And the reason this Gaussian function is normally used is because it's radially symmetric. And this was the equations for momentum. We keep a running average of the gradients. And every time we see a new data item, we update our running average, and then we use the running average to update the actual weights. Okay, we also looked at dropout. So weight decay is part of the. What weight decay can be seen as a way of trying to avoid overfitting. Dropout also tries to avoid overfitting. So this was where we randomly, when we train a mini batch, we randomly exclude a certain fraction of the nodes from the network, typically a half, and then the remaining nodes have to try to learn the task, and then at the end we put all the nodes back. We multiply each one by the same fraction in order to have the thing, the activations be the same size in terms of a mean field theory approximation. And we discussed how this weight decay was actually this very sophisticated idea, because in principle it's actually kind of ensembling over a whole. A very large number of different architectures. This thing on the right is one example of an architecture, and then there's a whole kind of ensemble of these ones that we're training over. Okay, so any questions about this? Right, then we looked at geometry and how to analyze the hidden unit activations. So we talked a bit about Hinton diagrams. We looked at this Hinton diagrams in relation to this early autonomous driving. We also looked at it in relation to early face recognition and pose recognition. And then we were looking at these limitations. So this is an example, a simple example of something that can't really be learned with a two-layer neural network. You're given the x and y coordinates of those dots, and you have to output 1 for the blue dots and -1 for the red dots, or 0 and 1. A 2-layer network just fails to learn this, but if you build a 3-layer network with these shortcut connections and you adjust the learning rate and everything appropriately and train it long enough, it will learn this data. And then we said, well, okay, so adding extra layers to the network makes them more powerful. Can you just sort of, could you add 4 or 5 layers to learn a task that failed with 2 layers? And then people in the late 90s recognized this problem. Well, it doesn't sort of work that way. So the networks that they were looking at the time that had these sigmoid activations and tan-H, if you add extra layers, it usually failed to learn, and because of this problem of vanishing and exploding gradients, it becomes very finely balanced, and there's a big risk that as you backpropagate through the network, either the differentials go to 0 or they blow up occasionally to large values. So we looked at a number of different ways to address this problem. So these included well, we'll get to these in a minute, batch normalization and weight initialization, and also the unsupervised pre-training that we talked about near the end of the course also fits into this framework. That was another way that people dealt with this issue, was that they would train the network with a deep Boltzmann machine, as a deep Boltzmann machine or an autoencoder, layer by layer initially, and by doing that, and then they could use backpropagation, and that would succeed even with the old-fashioned sigmoids. But then people sort of said, well, if we get rid of the sigmoid and replace it with a rectified linear unit, or a scaled exponential unit, then we seem to be able, that also seems to solve the problem of vanishing and exploding gradients, and does a pretty good job, at least for certain tasks, such as image classification. So, speaking of image classification, we started talking about convolutional neural networks. So how you can build up a network with, typically you have a convolutional layer and then a pooling layer, and ... So you might have a second convolutional layer and then another pooling layer, and then eventually you have some fully connected layers and then the output. And if it's image classification, then we need to, if it's any kind of classification, but this arose in terms of image classification, we looked at the softmax cost function. So this is on the assumption that the probability is proportional to the exponential of the corresponding output. And if you work through the example, that I think they put an example in the exercises that kind of shows how this works. So it's always kind of nicely balanced, that it increases the correct output by a certain amount, and it decreases all the other outputs by amounts which add up to this. So the increase and the decrease always balance each other out. If you add up all the decreases, it corresponds to the same as the one increase. And the decreases are proportional to the size. So if there's a wrong answer that's got a very large output, then that's the one that gets reduced the most. Right, so then we went through how to do the geometry and the mathematics of these convolutional networks. So we went through how you have this sliding filter that goes across the image or the previous layer and computes the values in the next layer, and we can write it as a summation like this, and then we looked at what happens when you have different strides and zero padding. So the most general case we considered was where you have both stride and padding, and you can use these formulas to figure out how many neurons there are going to be in the next layer. And we also looked at how to compute the number of weights and the number of free parameters, and sometimes we have a bias and sometimes not. So I think in the first assignment we didn't have the bias. It's sort of sometimes included and not, depending on the situation. And we had a bit of a look at how you can use kind of Hinton diagrams to get an analysis of these hidden units. Well, the first layer is definitely a Hinton diagram. The second and third layer, it's kind of somehow relating it back to the original image. You know, it's trying to say what image would this node would respond most strongly to. Right? So it's perhaps not giving us all the possible information, but it's giving us a pretty good idea what's going on. Right, so getting back to these vanishing and exploding gradients. So there are a couple of different ways that people use to get around this. So one is this await initialization. So you go through this analysis where you figure out the expected kind of mean and variance of the activations at the different layers, and then if you initialize the weights with an appropriate from a Gaussian distribution with an appropriate standard deviation, then everything will be kind of in balance, and the differentials will neither explode nor vanish as you go backwards through the network. And we also looked at another related method, is this batch normalization, where you actually, for each node, you have a mean and a standard deviation. You have a target mean and standard deviation for that node, which are additional parameters that are learned by backprop, and so you calculate the actual mean and variance, and then you shift the distribution to make it equal to the new mean and variance. And then if you want, so all of these are kind of lumped together as strategies for building deeper and deeper networks. So if we get really deep, then we have to start introducing new things like residual networks and dense networks. So if you remember the residual networks, the pre-activation is kind of copied over here and added to the output of so these two layers here are not computing the new activation, but just what should be added to this in order to get the new activation. So they're computing a residual, and from trial and error, it was figured out that having two layers together like this was kind of the optimal configuration. And then people looked at dense networks where you have a little dense block. So again, this idea kind of goes back to the twin spirals where we had all these shortcut connections. So here again we have shortcut connections, but again the way it's done is you have a little block and you have everything, all the layers connected to each other within the block. And then you often have a pooling layer afterwards. And finally, we looked at this example of neural texture synthesis, where you take the content of one image and the style of another image and merge them together, and it looks like you're standing in a Van Gogh painting. And we looked in a little bit in how this is achieved. So It takes the feature maps and computes the gram matrix for the pairs of features. And then the backpropagation is actually done to alter the image itself in order to minimize this combination. So the L2 distance to the content image plus the distance between the gram matrix of the style image and the gram matrix of the new image. Okay, any questions about this? Good. Then we moved on to recurrent networks. Yeah, so we looked at processing temporal sequences. We looked at the sliding window of approach of NetTalk, simple recurrent networks, how to analyze hidden unit dynamics, and then like long short-term memory and GRUs. So we looked at the NetTalk system from 1987, where you just only could see 7 characters at a time. And then this simple recurrent network where the hidden nodes are copied to the context nodes at each time step. And this can be trained through backpropagation by time, through time, so how to unroll the recurrent structure to make a longer feed-forward structure. And we did some analysis with networks trained by simple recurrent networks trained to do these simple languages like AN, BN. We saw how they would oscillate towards an attractor and then oscillate out from a repeller, and A and B and CN. Then we talked about how we needed more long-range dependencies, and you get this through LSTMs or GRUs, and we had this, we looked at how this works. So this is a combination of a forget gate, an integration gate, and an output gate. And you've got the gates. The gates always multiply each component by a number between 0 and 1, so that's why these are always used. You always have a sigmoid when you have a gate because you want a number between 0 and 1, but the actual values, you have a tanh because you want a value between -1 and 1. Yeah, and then the gated recurrent unit is a similar idea, but only has 2 gates instead of 3, and there's been an ongoing debate about. For a while, people were saying that graded recurrent units did as good a job as LSTMs, but some of the latest research is now people are claiming that LSTMs are actually a bit better than GRUs. So then we went on to language processing. So we looked at how to extract a co-occurrence matrix from a long corpus of text, and how you could extract word embeddings. So we looked first at how to do this with singular value decomposition. You do the singular value decomposition of that co-occurrence matrix, and the first k rows of the resulting matrix give you an embedding of the words into a k-dimensional space, but it's too expensive to do this for a language task because we've got 50,000 different words. So then we can achieve something similar using this word-to-vec model. And we looked at word-to-vec. So it's remember it was a linear model. You had a 1 in n encoding at the input, and then you had this hidden layer effectively became the word embedding, and you look at, it's meant to predict what words are likely to occur within the context of other words, and we saw how this can be applied in 2 different ways, the skipgram model, the bag of words model, but as far as the output is concerned, if we've got 50,000 different words, normal softmax is too expensive because we would have to compute all of those 50,000 outputs. So then we looked at two different alternatives for reducing that dimensionality. So one of them was hierarchical softmax. So this puts all the words into a binary tree, or a Huffman tree, and then they managed to figure out this notation that actually captures captures the thing. So this is where the probability. So you're looking at the probability of the correct word being predicted, and the word occurs somewhere in the tree, and so the LW is the depth at which it occurs, and these NWJs are the nodes that you go through in order to get to that word, and each of these has its own vector, and H is the output at that particular time, the output of the network. And so this inner product here, this inner product tells you how close those vectors are to each other. And then this notation here is meant to be plus or minus 1, depending on whether this is the left child or the right child. Yeah, so this gets multiplied by plus or minus 1, and then we compute the sigmoid, and that gives us a probability. Yeah, so the notation is, I think they had to struggle hard to think of appropriate notation, but it all kind of makes sense. And it gives you a genuine probability. It's mathematically pure, this model, because at each branch of the node, you've got a genuine probability. The probability of going left or right adds up to 1. And so the whole thing is a genuine probability. Now, this negative sampling is simpler in some sense, but it's not mathematically as rigorous, because it can't be literally interpreted as a probability. This was just saying, well, this is the word that actually occurred, and then we're going to choose some other words randomly that didn't occur, and we're going to increase the output for the word that did occur and decrease the others. So then this gives us, once we've got those embeddings, we can use them to do word vector arithmetic. So we looked at, how to extract out things like capital cities or largest city or president of a country or first names and last names and all these different relationships. And we talked about how this could be generally used to answer questions like A is to B as C is to what. You compute the difference of those vectors and then look for the one that has the smallest angle with that combination. And finally, we looked at a couple of more kind of industrial size language processing systems. So we looked at the bidirectional recurrent encoder. We looked a little bit at the Google neural translation system, and this idea of an attention mechanism where you assign weightings to these hidden unit values as you translate the sentence or develop a caption for an image. Any questions about this? Yes.
About the hidden unit oscillation.
Yes.
How can it grow by hand?
So what was the question? The hidden unit activations.
The diagram, how can it grow it?
How do you grow it? Which slide? Tell me when to stop. Yeah.
Go back. Probably hidden unit oscillation or something.
This one here. Well, Okay, good question. So the question is, how do you stop the oscillations from growing without limit? So this is a prediction task. So there's two answers to this. So the hidden unit, tan H, is being applied as the activation function. So definitely the activations can never exceed +1 or -1. They're bounded within this box. But secondly, yeah, because this is a prediction task, it only ever deals with it only ever deals with strings that actually do belong to the language. So if it's presented with 7 A's, it will be presented with exactly 7 B's, and then it will be presented with another A. So the behavior of the network, if you presented like 7 B's and then 10 A's, the behavior of the network would be indeterminate in some sense. So it raises good philosophical issues, what you're saying. Like, on the one hand, it's not going to explode because it can never. Well, I guess what would happen is these activations would still So after here, it would go to here, and then it would keep oscillating, but it can't go out to infinity because the tan H will always bring it back inside the box. So eventually, it would just oscillate back and forth between these boundaries. But the question you ask also raises an interesting point, that if you train a system to deal with certain strings of inputs, then there's always like, if you give it some input which is really just totally different from what it was trained on, it's hard to know what the behavior is going to be, because it's kind of relying on the fact that the input will be of a certain type. Yeah. Is that a satisfactory answer? Yeah. How can you draw it by hand? Yeah, you just have a bit of practice. It's not. It doesn't have to be, a work of art. It just has to roughly look like this. It doesn't have to be exactly the same. Just something oscillating and then another thing oscillating outwards. Yeah. Good. So then what? Then we moved on to reinforcement learning. Right, so we've had this general reinforcement learning framework. So we have a set of states and a set of actions. And at each step, we're in some state, and we choose some action, and then we go into another state and receive a reward. That's the environment, and then the agent has a policy which says what action it will do in a particular state, and we tried to, in general, these all can be multi-valued with a random element, and I've tried to, that's why we use these curly R, and I've tried to keep the notation consistent, that it's always includes this probabilistic element, because in fact with the deep learning most of the environments that we deal with are probabilistic, right? So each of these is actually becomes a probability distribution, a conditional probability distribution, given the fact that we were in state ST and did action A. What's the probability that the next state will be this? We get a probability distribution over the set of next states, and a probability distribution over rewards, and the agent, if it so chooses, can have an action, can have a policy which gives you given a state, it gives you a probability distribution over actions. We talked about different models of optimality and the sort of finite horizon and the average reward, but most of the time we deal with the infinite discounted reward. So we think about rewards going all the way to infinity, but we have a exponentially decaying discount factor. So we looked at a few different approaches to reinforcement learning. So we looked at value-based methods where you're trying to learn a value for a state or a value for a state and action combination. So we had TD learning and Q learning. And then we looked at policy learning where you're not learning the value, but you're just learning the policy directly. So we looked at policy gradients and the hill climbing and the evolutionary strategies. The hill climbing and hill climbing is a kind of special case of evolutionary strategies. Those two things are closely related, but these are also fall into policy learning because they don't make explicit use of a value function except to choose the actions. And then we looked at combinations of the two. So this actor-critic methods was actually where you have a value and a policy and you learn both of them simultaneously. We talked about the exploration-exploitation trade-off. So that in order to guarantee learning the optimal policy, you have to sometimes choose an action which is not the one you think is best. And we looked in some detail in one of the exercises about why that's true. And the usual thing is just to the sort of epsilon greedy strategy with probability epsilon, you choose a random action, but sometimes people use this Boltzmann distribution, which is similar to softmax. Right, so temporal difference learning and then Q learning. So temporal difference learning, we try to learn a value function for each state. This is normally used in situations where we know the world model, so we know the transition functions. So we're in a state, so we consider the possible actions we could do. We look at the states we would go into if we did each of those actions. We look at our estimate of the value of each of those states and we pick the biggest one. That's how we choose our actions. And then we update our value function by, we compute the reward plus our estimate of the value of the next state discounted by gamma. And then if it's a deterministic domain, we could just use that as our next estimate. But if it's stochastic, we instead just do a kind of weighted average based on this learning rate. Yeah, so the new value is weighted by eta, and the old existing value is weighted by 1 minus eta. And sometimes we saw the same thing in a slightly different notation. Then we looked at Q learning. So this is very similar, except it's a bit more involved because the Q function depends on both the state and the action. So in this case, we have a Q function. This applies even in situations where we don't know the world model. We can still do Q learning because if we're in a particular state, we have an estimate for every possible action. We have an estimate of the Q value for the current state with that action, and we just pick the biggest one. And then for the learning, very, very similar to TD learning, except we look at the state we've moved into, and then we look at all possible actions we could do from that state, and among those, which has the biggest Q value, and that's what we use to plug into our estimate for the next, our new estimate for the Q value. So it's the reward we immediately received plus the maximum Q value available from the next state. Okay, so they were value-based, and then we looked at policy-based methods. So the most fundamental of these is policy gradients. So we particularly looked at this in relation to domains like Pong, where we just win or lose. So the outcome is, eventually the game ends, and then we just get +1 or -1. And so what happens here is, so intuitively, if you win the game, then you want to try to basically every action that you did along the way gets equal credit for the victory. And if you lose, then every action gets equal credit for the failure, right? So for every single action that you chose, you say, okay, I want to increase the probability of selecting that action next time, or decrease it if you ultimately get the -1. So that's why this is the log of the probability of selecting that action, or the probability of selecting the same action next time that same state occurs. And we look at the gradient of that with respect to the weights, and we add that all up for every single action, and then this R total is either + or -1. And then we saw that if we subtract off a baseline, that actually makes the learning quicker and more stable. So in the case where the R is either + or -1, we don't need the baseline. But if you were in a situation where you get 5 points if you win and 3 points if you lose, then this equation eventually it will converge, but it takes a long time, because even when you lose the game, it's still increasing. It's still increasing the probability of those actions, but it's not increasing them by as much as if you had won the game. So you're going to learn faster if you say, okay, well, sometimes I'm getting 5 and sometimes I'm getting 3. On average, I'm getting 4. So the times that I get 3, I actually want to decrease the probability of those, because I'm getting less than what I should be getting. Yeah, so this is the baseline. And that's the reinforced algorithm. Then we looked at deep Q learning. So you guys have just finished the third assignment, so you've probably looked into some of these issues. So again, you can improve the learning by having this experience replay, because if you're playing a game and you just learn the thing in the same sequences that you're playing, then you're seeing kind of similar situations repeatedly. So you get a better result if you play games and put them into some kind of database and then sample from the database. So you're sampling from different games in a bit of a random order. And then we looked at double Q learning and advantage actor critics. So again, some of these things really emerge out of trial and error. I guess the motivation for this double Q learning is a little bit sort of subtle, but it's based on the idea that you're using this, with normal Q learning, you're using the same Q values for two different purposes, one for selecting the actions and secondly for learning the value function. And because of that dual use, learning somehow becomes a bit unstable. So you can deal with this by having two different sets of Q values and using one for one purpose and one for the other. Or they found that they could, instead of using a totally separate Q function, they could just use Q functions that were a little bit delayed and aggregated from other nodes. And then finally we have this advantage actor critic, right? So this combines policy learning and value learning and we treat this, it's called advantage because we treat the value function as a baseline. So remember the QSA is, the VSA is theoretically the value we would get if we chose the best action, and then this Q function is what we get if we choose a particular action. So this advantage is the difference between choosing this action and choosing the best action. So it sounds a bit, you have to get used to the sign. It seems a bit funny because this value will often be negative, right? This is the negative, this is the amount that we're losing by choosing a bad action, it could be, right? So, but we call it an advantage. We call it an advantage anyway. Well, in the early stage of learning, it may be an advantage, but once in the late stages of learning, this is often going to be negative, but we still call it an advantage, but if it's a negative, it's really a disadvantage. And again, this is just what emerged as the best way to do things after trying several variants. So they learn the value function by TD learning. They learn the Q value. They keep they keep the entire sequence of actions and rewards in memory, so they get a bit of a better result if they use a whole sequence of n of those, a sequence of n rewards rather than just the most immediate reward. And then the policy is updated to maximize. You take the log of the probability of selecting that action again and multiply it by the advantage that's provided by choosing this action compared to choosing some other action or the best action. And then this is, the value function is updated by minimizing this. So the Q function is, if we're playing the game several steps ahead, we're assuming that we're making good choices after the current move, and so the average of this over time should approximate the value function. Good. Then we looked at hill climbing, and we saw that this is kind of it's a kind of reinforcement learning. I don't know, traditionally some people may not have referred to evolution as reinforcement learning, but it is in the sense that it's tackling this, it's an alternative method for tackling the same problems. And so we looked at this sort of hill climbing algorithm where we have a champ policy and then we generate a mutant policy. We compare the champ with the mutant, and then if the mutant does better than the champ, we adjust the champ some way towards the weights of the mutant. So this was the kind of simple algorithm that we developed in the 90s, and we applied it to simulated hockey and backgammon. And then this is the slightly more, perhaps slightly more refined algorithm that was used last year in this OpenAI paper, which is very similar, except that instead of the amount by which you move towards the mutant depends on the fitness of the mutant. So if the mutant is, so in the early algorithm we just said, okay, there's some threshold, and if we're above the threshold we'll move 5% towards the mutant. If we're below the threshold we won't move at all. So this version you always move towards the mutant. Well, you always move, but the amount by which you move depends on the fitness of the mutant compared to the average fitness across multiple mutants. And so if this mutant gets a particularly high fitness, then you move very far towards it. if it gets a particularly low fitness, you actually move backwards away from it. Okay, and this was applied to Mijoku and humanoid walking and various other things, and it was parallelized across 1,440 cores. Right, so that was reinforcement learning, and then we moved on to the third part of the course, which was unsupervised learning. So the first example we looked at of unsupervised learning was the Hopfield network. So we have this energy function where there's this weight matrix that basically, so the xi and xj are always plus or minus 1, and then if the weight matrix tells you whether those two neurons are likely to have the same value or opposite values. So if the weight, if wij is positive, then that tends to make those two, it tends to make xi and xj have the same value. If wij is negative, it tends to make them have opposite values. If wij is 0, then the network doesn't care whether they're equal or unequal, right? And so the network gets updated according to these equations. So the update can be either synchronous or asynchronous. If it's synchronous, you update everything at once. If it's asynchronous, you update them one by one randomly. But you always pick one particular xi, and you ask yourself, well, could I lower the energy by changing the value of this xi? And if you can lower the energy, then you change it. And then this was sort of leads on to the Boltzmann machine. So these two things, the energy function looks exactly the same. The formula looks exactly the same, but the dynamics is a little bit different because the Boltzmann machine, the values are 0 and 1 instead of plus 1 and minus 1. So we kind of lose that symmetry, but we can think of these values as being features that can be present or absent. And this turned out to be too kind of difficult and lengthy to train. So, there's all this sort of mathematical theory that goes behind the Boltzmann machine. But it turned out to be too difficult and lengthy to train. So then they introduced the restricted Boltzmann machine. So the original Boltzmann machine, everything's connected to everything else. The restricted Boltzmann machine, you divide the nodes into two groups. There's the visible nodes and the hidden nodes, and every visible node is connected to every hidden node, but the visible nodes are not connected to each other and the hidden nodes are not connected to each other. So this makes the updates a lot simpler because the energy, if I'm looking at one of these nodes and I'm thinking about changing this node and I want to know whether it'll lower the energy or not, I only need to consider, if I'm changing this, I only need to consider these values and not the other ones. So these can all be considered in parallel, and then these can all be considered in parallel. They don't interfere with each other. So it gives us this algorithm where we fix these and change all of those, and then at the next step we fix these and change all of these, or potentially change all of these. And the energy function then is written like this because the W is 0 if for a hidden and hidden combination. So the W's are only left if there's a visible node and a hidden node. But we have these biases. So with the Hopfield network, we often set the biases to 0, but with this Boltzmann machine, those biases are actually important. Yeah, so there's biases for the hidden nodes and the visible nodes. And we trained it by this alternative Gibbs sampling. Hidden as I said, fix the input, change the hidden, fix the hidden, change the input, back and forth. If you do that enough times, eventually you'll get you'll be sampling this eventually this combination of these hidden and visible nodes will be like a random sample from the Boltzmann distribution. So people were training like this, but again, it took a long time if they want to go back and forth several times. So then people in Hinden's group in the early 2000s introduced this sort of quick contrastive divergence where they just do 3 hops. And so again, again, now we can sort of step back and see a bit better these connections between different parts of the course. So this is a little bit like, if you remember hierarchical softmax compared to negative sampling, the negative sampling didn't have a formal mathematical reasoning behind it, but gave reasonable results. This is comparable, that because you're only taking these 3 hops, you're not actually sampling from a genuine Boltzmann distribution, and so you've got your actual distribution, and then you're sampling something which is just a little bit away from it. So you're kind of you're training away from these. There is a risk. You're training on negative samples that are just a little bit away from the real manifold, but there's a risk that you might not be training on other negative samples that are further away. So theoretically, you can't really prove much about this, but in practice, it actually gives pretty good results. Then we looked at autoencoder networks. So this is where you train it just so that the output reproduces the inputs through this bottleneck. And we saw that we talked about this mainly in regard to images. So we talked about how you have the need for regularization so that you don't just learn an identity mapping, because these convolutional networks have a lot of nodes and a lot of parameters. And we looked at a few different ways to regularize these things that are discussed in the textbook. So there was sparse autoencoders with dropout, contractive autoencoders, and denoising autoencoders. And then this kind of moved on to generative models. We're nearly done. So the first example of a generative model that we saw was a variational autoencoder, right? So what was the purpose of these generative models? Well, again, it's easiest to think in terms of images. I give you a bunch of images. I want you to generate new images which are not exactly the same as the images I gave you, but are similar in style, right? So if I give you images of dogs, I want you to generate new things that look like images of dogs, right? And so if I want to generate a new image of a dog, I want to just be able to choose a random latent variable z from a Gaussian distribution, and if I feed that in, a picture of a dog should pop out the other end. Right? So we looked at variational autoencoders, and then we looked at generative adversarial networks. So the variational autoencoders, we had a mean and a standard deviation for each pixel, and this can define a conditional normal probability distribution. And this was the cost function that it's trained on. So that first term says that right. So in the first term, you're choosing a latent variable and you're generating an image sorry, in the first term, if you're right, so if you feed in an actual image and it produces a latent variable, then if that latent variable is fed into the decoder, it should produce something that approximates the original image. So it has to reproduce the original data. And then the second term says that the encoder should produce latent variables which fit this fill out this Gaussian distribution, right? By based on the KL divergence from this distribution to the Gaussian distribution, right? So if an actual image goes through the encoder and then the decoder, it should get something that looks like the original image that was fed in, but then these latent variables can't just kind of bunch up or collapse. They have to spread out to cover the Gaussian distribution. So this is the idea with a variational autoencoder. Maybe it's a bit difficult looking at these equations, but then when we look at a particular example, it makes a bit more sense. So this kind of looks like a Gaussian distribution in 2 dimensions, or if this started out in higher dimensions and got projected onto 2 dimensions, we'd expect it to look like this as well, because you could see there's sort of higher density in the middle than at the edges. And this has been trained on the MNIST data set, and you can see how it does actually kind of reproduce digits from different parts of this latent space. And then finally, we looked at the generative adversarial networks. So here, this is where we have a generator and a discriminator. So the discriminator is a convolutional neural network. The generator is a deconvolutional neural network. So you feed in latent variables and an image, it produces an image. And so the discriminator is trained to try to assign a high value to the real images and a low value to the fake images, and the generator is trying to produce images that the discriminator will assign a high value to. So that becomes this kind of zero-sum game. And in the last 2 lectures, which were extension material, but we saw how this fits into a much bigger framework of zero-sum games and game theory and artist-critic coevolution and other things, right? And then we saw that actually it's not quite a zero-sum game because it's convenient to replace the second term so that the logarithmic blow-up happens at the other end of the distribution. But in principle, it's the same kind of idea. And this was we went through this actual pseudocode. So you sample an equal number of real images and random latent variables. So you sample M latent variables Z, and then you pick out M actual images. And so you train the discriminator on the positive and the negative examples according to this cost function. And then again, as I said, it's possible you could use the same latent variables that you had from above, but it actually gives slightly better results if you sample a new set of latent variables and then you feed those to the generator. That produces images, which you then feed to the discriminator. And in this step, you're not training the discriminator, but you're just training the generator to try to increase the score given by the discriminator. And you're actually you're back propagating through the discriminator into the generator, because there's an image in the interface between the generator and the discriminator is this image. Yeah.
Quick question. What are the latent variables again in this case?
Well, okay, so they're just variables that are drawn from a normal distribution. So every Zi is drawn from this bell-shaped curve with a mean of 0 and a standard deviation of 1. There's those latent variables. But I suppose a better way to think of it is if we think back to when we were just doing image classification, we had the image and then we had convolutional layers and pooling layers, and then eventually we had fully connected layers, and then we had an output layer, right? So here, if you chopped off if you forgot about the output layer and just looked at the last fully connected layer, those would be the latent variables effectively, but then the thing's going in reverse, of course. You're starting from there and going back to get the image. Yeah.
They all start from the same premise that the CNNs start from, which is like the RGB values, but it's down.
Well, the latent variables, who knows what they are? They're supposed to be completely. They may not represent color or particular parts of the image. It's hard to know what those latent variables really represent. It could mean, again, like if you're thinking about a bedroom, a latent variable could be capturing whether there's a window, whether there's a headboard, whether there's a bedspread, whether it's a single or a double bed. It's meant to be kind of very abstract features like it's good questions you're asking. So it's meant to be kind of very abstract features like that, and because the Gaussian is radially symmetric, it doesn't matter. Like it might not be that Z17 actually corresponds to whether it's a single or a double bed. It could be that some weird combination of Z values corresponds to that, because if every Zi has a Gaussian distribution, that's the beauty of the Gaussian distribution. If every Zi has a Gaussian distribution, then any linear combination will also have a Gaussian distribution. That's about it, I think. Okay, so yeah, and then that's so then we talked about the GAN image. So the variation autoencoder images were kind of fuzzy and didn't look that good, and then the GAN images were much better, and there's been all these improvements ever since then. I think there was some new paper by Google a couple of weeks ago where they're doing this on an absolutely massive scale with tons of computers and various other things. Good. So any questions, any other questions about that? Yep. Okay, the energy in the Boltzmann machines. So that's a good question. Well, if we think back to, let's first go back to the Hopfield network, because it may be a little bit more intuitive here. So with the Hopfield network, if we think of this as an image, and we think of +1 as white and -1 as black, then the energy function would be saying that if this pixel and this pixel have the same color, then we achieve a lower energy. You always want the lowest energy state, and if they're different colors, it would have a higher energy. So it can be thought of as some kind of force which tries to make these two pixels have the same color, right? But it's interacting with other forces. So if you think about this pixel and this pixel is some third pixel, maybe there's a force trying to get these two to be the same, but there's a force making these two different and making these two the same, and they could be interacting with each other. But somehow, like when you add it all up, you reach a configuration that tries to satisfy those constraints as well as possible. Yeah. Exactly, like entanglement. Yeah, you've studied physics. Yeah, yeah. Well, if you think about the Ising model, is this sort of the fundamental case of this. So then, except of course, it's not quantum. It's not it's not complex numbers. It's just real numbers. Now with the Boltzmann machine, yeah, to be honest, I've sort of struggled with this myself over the intuition, but I guess it's the same kind of idea, but we think of these not as pixels but as like features. We think of the hidden units not as pixels but as features. We could still think of the visible units as pixels if we want, with 1 is white and 0 is black. But the hidden units, we think of them as kind of features, and then I guess what it means is that each, how would we think about this? Like if you pick one hidden unit, it's connected to, if you think of one hidden unit, so let's think in terms of images. So you think of a hidden unit and it has weights connecting it to all these pixels. So a positive weight means that if a positive weight means that if this pixel is white, then that feature is more likely to be present. But if this is dark, then it's less likely to be present. So these features, there's sort of a reason, so they do sort of behave in a way like the features in a convolutional, in the first layer of a convolutional network, which is why they're sometimes used for pre-training. But then it's just sort of being applied in reverse. So it's trying to maybe extract out patterns in these images. Certain sets of if this feature is present, then it means that certain pixels are likely to be white and certain other pixels are likely to be black. So you start with the image, and then you just, so when you do this Gibbs sampling, based on the image, you probabilistically decide whether that feature is present or absent. And then based on which features are present or absent, you probabilistically draw another image, and you kind of go back and forth. I don't know. Because it is confusing, because the energy function depends on both the hidden and the visible units. And of course you can marginalize it and extract out a probability distribution on the inputs, but you've sort of lost a lot of the structure of the thing when you do that. Yeah. So I don't know if that's a good answer or not. Yeah. Yeah. Right. Yeah. Good. Well, okay, if you've enjoyed this course, these are some related courses. Some of you may have done some of these already. Yeah, so AI will be running next term. I think machine learning will be running in term 1 of next year. Some of these I'm not sure exactly which term they're going to run in. I think that there was an advanced machine learning course running this session. I'm not sure what's the future of that course is. And you could also choose a fourth year topic in one of these areas. So there's other people in the school too working on deep learning for medical images and text analysis and various other things. If you're looking for a thesis topic, I'd be happy to have a chat with you and suggest some things that will point you in the right direction. I apologize, a couple of you maybe have emailed me. I've been very busy the last couple of weeks, but I hope to have a bit more time available in the next couple of weeks to pursue these things. So these are some of the things I'd be interested in, possible fourth year projects, or we could talk about something else. The only other thing, I guess, is about the pre-exam consultation. So we think you said the exam's on the Thursday, the 8th. I'll probably have a session on the Tuesday of that week in room 201B between 12 and 2, if you want to come and ask any questions about the course. Yeah, I often find that 2 days before is usually a time a lot of people prefer to come, as long as they don't have another exam on that day. So I'll put that on the course website. Please fill in the UNSW My Experience survey if you enjoyed this course. And also, yeah, the assignment, we're trying to, Alex is trying to sort out some of the issues still arising out of the second assignment, and we're going to get onto the third assignment pretty soon. Any other questions? Yes?
About the last assignment,
Yeah?
I think that most of us have timing issue.
Uh-huh.
So Alex said that 500 should be done before less than 1 minute.
Yeah.
I'm not sure anybody can achieve this, but it's about 5 minutes. So would there be any consideration or any plan for that?
So what are you saying, that we should run it for longer, or that we should...
Yeah, in my experience and some comments on the forum, everybody was hard time for the speed.
So you think they should be run longer, or that?
Yeah, it should be.
Yeah, okay. We'll try to run them longer, and I think we're also going to run each submission maybe 4 times or something, just in case. I know some people occasionally their thing failed to learn, so we won't just run each submission once. We'll try to get do several trials. Yeah. Sorry?
I would have submitted it tomorrow if we could run it longer. Because
Yeah.
I purposely trimmed it down to hit that time constraint.
Yeah. Well, yeah. So you're saying that it doesn't train at all? Like, I think we're not going to run it for just 100. We're going to run it, I'm not sure, maybe 2,000 or something. But if you can learn within 100, you'll get a higher mark, yeah. Yeah.
You know, get best out of 4, or are you averaging over 4? Or still on
What do they do with the Olympics? Best out of 4. We'll look into that. Yeah.
Are you going to post your own solution that we can try to look at?
That would be really helpful.
Because I have no idea why it wasn't stabilizing.
I'll talk to Alex about that. We'll look into that. I don't know. Yeah.
I'd really appreciate it.
Or at least some ideas about what we did. Yeah. Okay. Well, thank you very much for your attention. You've been a good audience. Ah, yes. Yeah.
So for me personally, I'm really good at calculating
Ah, yeah.
those percentages of theory questions and combination questions. Outside or
Yeah, if you have a look at the sample exam, it gives a pretty good indication.
because I keep applying the when I'm trying to finish the quizzes and
Uh-huh. Yeah, I mean, if some people are more used to seeing mathematical formulas, but if you just kind of practice writing them out and stuff, right? And then it's helpful if you try to look at the equation and try to identify. So I think there's one question that says, here's an equation and so if you try to do that for every equation, look at it and like, what are the individual components, that helps you to remember it.
same image?
Well, no, I guess it's across.
A set of images.
Oh, sorry.
This is like a
Yeah, xi. Well, it's a random variable. So for any particular image, you've got a particular value of xi and a particular value of xj, and that gives you a particular energy.
So
Yeah, I
are
guess
they
in
both
this
pixels,
case,
or are they both
they're both pixels. So this is a pixel, this is a pixel.
from the same image?
From the same image. Yeah, I guess xi and xj are specific to the image.
So it's more
But
like
this w is something that goes across all images.
all images.
So wij is something that says, like, across all images,
It's the same.
are
value.
xi, are those two pixels likely to be the same color or different colors?
Hold on. So across all pixels, this weight determined whether or not
All images.
all images across all pixels. So this weight is only singular.
Not all pixels.
Not all
wij is specific to, it's specific to a particular pixel here and a particular pixel here. But then it's saying, like, across all images, it's this pixel and that pixel likely to have the same color, then w will be high and will be positive. If these two pixels are likely to have opposite colors, then w will be negative.
And how do you choose those two pixels? Are they neighbors, or are they just?
Well,
like
you just, for
every
every, well, in the general case, it could be, could have a w for every pair of pixels.
So just be a completely overlapping.
Yeah, exactly. Fully connected. I mean, the w, for pixels that are far away, w might be close to 0.
Right. So you're kind of like, if it's black here and it's black here, then the weight activates, and you're kind of like trying to draw a connection like that.
That's right.
Okay, and then how does like a set of images, training it on a set of images, reinforce that? Are you